I'll start with an introduction to effects in general. So an effect system is something that will track the actions that a program can take. So this can be something like resource use, memory management, exceptions in Java, for example, as well as algebraic effects, which is a control flow mechanism, if you're familiar with that. When you have an effect system, you'll typically see the effects showing up in type signatures for functions. So here in the right line function, you see on the right, we have the console effect annotated on the right of the function. And we can also have multiple effects. So a read file function might have an IO effect and the possibility of throwing a file not found exception. We can, of course, have no effect if we're dealing with a pure function, like concatenating two strings. And we can also have effect polymorphism. So when you map over a list with some function, that function f will have some effect here, ef. And then executing that map function is going to have that same ef effect. Now, what I'm interested in here in this talk is how do we integrate effect systems and type classes? And to show you why that's not hard, or why it is hard, I'll take you through a few examples. And the first example is with overloading arithmetic operators. So if you imagine that we can add floating point numbers, which is easy if you try, we might have a function like this specifically for floating point numbers. And then we can also have a separate function for adding integers together. But it's kind of annoying to have these two different functions for adding things when adding things is kind of the same everywhere. We want to be able to use just the plus sign for adding. And in a functional language, the typical way to overload an operator or a function is with the type class. So here we have an add type class, which lets us overload that plus operator. And then we can create an instance for each type that we want to add. So we have an instance for integers, and we have an instance for floating point numbers. And each of these delegates to that specific implementation that we had before. If you buy that, then you might also buy that we can divide floating point numbers. Here we have a special division operator for floating points. And it's not much of a stretch to say that we can also divide integers. But if you believe that, then you've been fooled, because we can't actually divide integers, at least not all the time. Integer division can lead to a division by zero error. But floating point division actually cannot if you're following IEEE RFC 700 something, which says that division by zero is not a number or it's infinity, depending on your arguments. So if we want to abstract over this like we did with the addition and define a division type class, we actually have a problem, because floating point division is total, but integer division is partial. So when we have this division by zero exception in dividing an integer, we need that in the effect signature. So what effect signature does division have? It can't be pure, because we need this division by zero, but it can't be division by zero because we need this, this purity for floating points. So more generally, the problem that we have is how do we make one type class abstract over both partial and total functions? So that was our first example. Another example is dealing with iteration over collections. In Flix, which is the programming language that I'm using here, a mutable data structure lives in a region. So here we have an immutable list, which is our standard cons list, as well as a mutable list, which has both an element type A and this R, which is the region where this mutable list lives. And that means that when we observe data in this list, we're going to have that region effect in the signature. So the pure head function for an immutable list has the pure effect. There's no effect. But the impure function for observing a mutable list has that R effect, the region of the mutable list. Now, if we want to manipulate this data, for example, by folding over it, well, folding over the immutable list is fine. We just have that a similar signature to what we had with map at the beginning, where we're polymorphic in the effect EF. But when we fold over a mutable list, we actually have this union of effects, because we're both observing the list and executing the effect of F. So again, we have a similar problem. If we want to generalize this folding operation, say with a type class foldable, then we end up with a problem because we have these mismatched effects. One of them is EF, and one of them is EF plus R. So again, more generally, the problem that we have is how can we make one type class abstract over both mutable and immutable data? And the third example I have is dealing with data streams. We have this reader class, which will read bytes from a resource into an array. The resource, it has type T there. It's called RD. And the effect of this is R, the array that we're reading into, plus IO, because presumably we're doing some IO operation to read. And this is appropriate for something like reading from standard in, because that indeed is an IO operation, and we're modifying the array as we read into it. But for something like a string reader, well, reading from a string isn't an IO operation because the string is not any kind of IO thing. It's just some mutable value, or the string reader is a mutable type. And so the effect of this is R plus R1, not R plus IO. So once again, we have these incompatible effects. So problem 3 we have is how can we make one type class abstract over different element types, or different effects of effectful operations. So to summarize our problems, we want to be able to define type classes that abstract over the effect signatures of partial and total functions, mutable and immutable data, effectful operations, and there are several other problems that I won't show today. The solution that we propose to this is something that we call as an associated effect. And this is an effect that we associate with a type class, and we select it for each instance. And we'll go back to that first example to show you how it works. Here, again, we have this div class, but in addition to the div member function, we have this type AEF, and this is our associated effect. Then in the signature of div, on the right-hand side, you see in the effect position, we have AEF. Now, when we implement an instance of div, we're going to select what that associated effect is. In the case of integers, that's going to be division by 0, because as we established, integer division can lead to a division by 0 exception. In the case of floating points, we're going to define the associated effect as pure, because floating point division is total. We can do the same thing for foldable. Again, it's a similar solution. We will add this associated effect, and then the effect of fold left is going to be the union of EF, the function f's effect, and our associated effect. So when we fold over a immutable list, we define AEF as pure, and therefore our effect is just the effect of f. But when we fold over a mutable list, our effect is the region R, and so our overall effect of fold left is going to be EF plus R. And finally, the story is the same for that reader. Here we will define the effect as R plus AEF. Then the standard in reader will be R plus IO as we had before. But for the reader of string reader, we define AEF to be the region of our string reader. And so the read function has the effect R plus R1. So that's the theory. What about in practice? So we have a full implementation of this in the Flix programming language. And we've expanded the standard library, first with a refactoring and then an expansion with what we've unlocked with associated effects. So briefly about Flix, it's not a toy language. It's actually a proper language by some measure with a bunch of features, including standard things like algebraic data types and non-standard things like first-class data log constraints. And again, just as evidence of it's not being a toy, we have several thousand, 100,000 lines of code, a bunch of library functions, and a bunch of library lines of code. We made a lot of changes to support associated effects, but they were fairly simple changes with modified classes to add these associated effects to them, modifying the signatures to include those associated effects, and function signatures that use those type classes. Thanks to this refactoring, we were able to define instances for mutable data types. So for iterable, foldable, unordered, foldable, and toString, all of these classes were previously only defined for pure data types due to this inability to abstract over the effect. But now we can define them for all these 7 extra mutable data types, in total getting 28 additional instances in our library. We have a calculus for this, which I will not present at all. But it's based on this work, Associated Type Synonyms by Chakravarty and friends. And if you're interested, you can take a look at our work and their work. So in summary, I've presented associated effects, which are an integration of effects and type classes. They allow for abstractions over partial and total functions, as well as over mutable and immutable data, and abstractions over effectful operations. Our contributions include the idea of associated effects, as well as the type system and implementation, and the expansion of our standard library. For more information, you can check out flix.dev. And that's all. Thank you.
Okay, I think we have time for a lot of questions.
Did you try implementing something like this in Haskell, or simulating it in Haskell on top of, I don't know, associated types or some other features?
No, we did not attempt that. Indeed, this, of course, bears a lot of similarities to associated types, and Chakravarty's work is...
Do you have reason to believe it would not be doable there, or
I have no such reason to believe, no.
So it may well transfer
I think so,
to
yes.
other type class systems. Okay, thanks.
Mm-hmm.
Hey, thanks for the great talk. I can imagine you might find yourself in a situation if you're writing a new trait, basically, that you're sort of defensively adding a associated effect because who knows what the implementer might require. Sure, it can default to pure or whatever.
Yeah.
And on a related note, I'm aware of a sort of nascent initiative in the Rust language that it's sort of targeting API compatibility. And I think you can basically think about it as they're adding associated effects to the instances, to the implementations, but they're not present on the trait. So the idea is that you can sort of like implement a trait in a context where you couldn't normally do it. So how are you approaching thinking about this in terms of like, API design and things like that?
Sure. So there are a couple things. So one is there are certain traits where you definitely do not want, or very likely do not want to have associated effects. And one example, for example, is equality. It's usually bad for equality to have an effect because if you're searching through a list, you don't want to have to execute a bunch of effects while looking for this this item in the list. So that's one thing. We are aware of some efforts in Rust. I think, for example, they have this trait that's async iterable and regular iterable, things like that. And it definitely seems like very much related to what we're doing here. I don't quite remember what the other part of the question was.
I mean, I guess the question was, equality is a good example of where you might not want one.
Yeah.
But, that one's very straightforward. I guess, like, did you find yourself, for example, when you were adding, associated effects to the standard library, being like, well, I can't quite think of what the effect might be here, but it cost me basically nothing to add it, so I might as well just do it.
I think when we were dealing with the standard library, mostly we were dealing with mutable and immutable data types. And so there it was very straightforward. It's going to be the region where our mutable data type lives. But I can indeed see that kind of defensive thing could be an interesting problem.
Okay, thanks.
Hi, could you please underline what are the differences or different issues that you encounter with associate types compared to just associate types? Effects and types, because it seems like very similar thing. So what's the difference really?
Yeah, so indeed it is very similar. And it's effectively just the placement of where it is in the signature. And so our contribution here isn't that associated effects is like a whole new thing compared to associated types, but rather it's identifying it as kind of a very important thing to realize that you want to have when dealing with type classes and effects. So in terms of a difference, there's almost not one, but it's rather identifying this as an important feature.
Okay, thanks.
Hey there. So my question is, if the mechanisms that you have to prevent certain, let's say that you have a function and you don't want this function to have an I/O effect and you want to prevent that to have that effect, is that the same mechanism that the underlying language uses for associated effects? Or
So
if you want to enforce some effects to have some or not have some others in a function?
So if you're just dealing with a function rather than a type class?
I mean a type class, yeah.
Sorry, can you repeat the question?
So let's say that I have a type class, and then I have the inner type T, and then I have this function, and I just want it for certain types that do not have a certain effect. So is there any mechanism for preventing functions to have a certain effect with associated ones?
So are you saying that the type class itself needs to say that no instance can have this effect, or?
Yeah. I don't want it to have this effect, but I want the other
To allow
types.
any other effect?
Yep.
Yeah, so Flix actually has this idea of effect exclusion, which you can see in a previous paper by us, where you can explicitly say, I don't want it to have, for example, the throw effect or some specific other effect. And that is possible with these associated types.
And it works perfectly with associated effects, right? Okay,
Yeah.
Very cool.
Can you flip back to one of the slides that declares an instance that has an associated effect?
Sure.
I have a syntactic question.
Okay.
I noticed that when you declare like the associated effect, it's parameterized by the same thing that the type class is parameterized by, but in all the examples, like it's just the same. Is there
Yep.
a case where the second thing would be different?
There is no such case. It has to be the same. And in fact, in a previous version of the slides, I did not include that in the syntax, and then I was told that was confusing. So yeah, it's always going to be exactly the same.
Okay, makes
Yeah.
sense.
I think that whoever made that suggestion was wrong.
Okay.
Can I ask a question? And then
Yeah.
you can repeat it because
Sure.
I can't go there. Why associated effects and not maybe parameterizing the effect within the type class? So
Yeah.
if we're sticking to the same slide, why don't you do class reader T, comma E or something like that?
Yeah,
If
so
you could repeat the question
Sure.
so that it comes up.
yeah, so the question is, why don't we use multi-parameter type classes, right? So there are a number of advantages and disadvantages. The main thing that we're concerned about here is that the effect is uniquely determined by the type. And so we don't want to have a situation where there could be overlap or anything like that. It's really a one-way kind of a function rather than a relation. And so in this case, associated effects is, or associated types or effects is the most appropriate thing in our opinion.
Okay, so let's thank Matthew.